Thank you. And thank you very much for coming. What I will be presenting today is results of more than 30 years of work of our Permafrost lab at the Geophysics Institute, University of Alaska Fairbanks, which I was working and still actually involved. So it's not only my research, but it's a big group of people, very dedicated scientists who collected data, which part of it, small part of it, I will be presenting today. Just to start, a couple of words about definitions. So permafrost, you probably, if you live here in Alaska, you're pretty familiar with what it is, but scientifically, it defined in different ways, but for me as a geophysicist, the most, and it's actually most common, most convenient way to define permafrost based on temperature. So it's any earth material which is at or below 0 degrees Celsius for 2 or more consecutive years, that's permafrost. So it's kind of formal definition, but it's convenient, especially for geophysicists, because it's very, very straightforward. If it's below 0 degrees Celsius for 2 more years, that's permafrost. And of course, it's not the best definition, maybe, because it doesn't say anything about if it's really frozen, if there's ice or not. But let's use it now, and we'll talk about ice as well. So it's product, so this is a map of permafrost distribution in the northern hemisphere. Everything colored is permafrost, and gray is non-permafrost areas. And the different colors just say some of the permafrost is continuous. That means you will find permafrost pretty much everywhere in that area, which is kind of bluish. And discontinuous, other colors, green, yellow, red. It means like Fairbanks area. So it could be permafrost in one place and non-permafrost in another place. And it's normal. It doesn't mean that permafrost is disappearing. It's just because of climate is such and conditions, surface conditions, vegetation, and so such that in the same climate, because of this variety of conditions, you can have permafrost in one case, or in one place, or non-permafrost in another place. So obviously, we can see even from here that permafrost is product of cold climates. So most of it in high latitudes or high elevations, but for the same reason. Low air temperatures, that's the key. Because of that, permafrost is, well, depending on cold climate. And because of that, when climate is changing, permafrost is changing as well. So if climate is cooling, permafrost feels good, extending. If it's get warmer, then permafrost is shrinking, not stable. So it's following climate, not directly, not one-to-one. There's definitely some delay, but on a big kind of scale, time scale, it follows climate pretty good. So that's pretty much enough for definitions, but that's about temperature. And temperature is, it's like I said, very convenient and very important parameter of permafrost, because farther below 0, like -5, -10, it means that permafrost is stable and we shouldn't worry about it too much. But if temperature is rising close to 0 degrees Celsius, that's something alarming happening, and permafrost may, became unstable and start to thaw. And so that's why temperature is very good parameter to follow and to estimate how stable permafrost is and how it's changing in time. So temperature is important to recognize what is stability in permafrost. But on the other hand, and I mentioned about it, there is very, very important other property of permafrost is how much ice is in it. And how much ice in it is exactly very important for consequences of permafrost disappearance. So if there will be no ice in the material, it doesn't matter if it's below zero, above zero, there's almost no difference in physical properties, and you will not notice pretty much almost anything. However, if there is ice, and if it's lots of ice, for example, on this photo, so in this photo is all this white stuff is ice, and dark is frozen permafrost or frozen ground. In this case, of course, ice included in permafrost, so it is all permafrost, but the white is almost pure ice. So in this case, if you have lots of ice, of course, the 0 degree is really crucial threshold, because, well, we know ice will melt when temperature will come close to zero and try to exceed 0 degrees Celsius. It will not exceed, though, till all ice melts. So temperature is important for stability and understanding where permafrost is going. The amount of ice is really important to understand what will happen if permafrost will be degrading. So I'll just would like to show several more slides where show the almost like ultimate case, how much ice it could be in permafrost. So how much ice it could be in permafrost? Well, from pretty much zero in bedrock, because by definition, by temperature definition, it's still permafrost if it's below 0 degrees Celsius, to 95% by volume. And that's what several, I would like to show the slides, which will convince you that it is the case. Like this, all white is permafrost. In between, it's frozen ground, which at least another 50% of the volume filled with ice. Some of these pictures are taken from Alaska, some are from Siberia. This is a Siberia picture. This is also a very interesting photo showing that how, well, it's whole, could be a whole another lecture, how this ice got into permafrost and what shape it could be. But one of the most common, especially in Alaska, form of ground ice, more or less pure ice, is ice wedges. So ice wedges formed because of cold climate, cracking the ground, filling these cracks every year, summer with melt water from snow melt, developing small lengths of ice vertical, which goes down to 5 meters. I will mostly say meters. If you would like, I can switch to feet. That, you know, but as a scientist and European origin, meters still more convenient for me. But you know, you can do it. If not, I can try. 15 feet. How about that? And every year, very, very tiny, like maybe 2 centimeters ice vein will appear, and then next year, and next year, and next year, and eventually it can grow like this. But what is interesting that, oops, sorry, if you look from the surface, these ice wedges develop so-called polygons, ice wedge polygons. And they could be different shape, rectangular or maybe hexagons or pentagons. It depends on property of material, really, and thermal conditions. But looking from the top, it's actually formed some sort of like a honeycomb thing, where the honey is actually less ice, and the borders it's ice wedges, so lots of ice there. And you can see this is taken from the same place. This cliff that's what you see as a cross, but on the top it looks like this, so ice wedge polygons. And I will mention about these ice wedge polygons. We will be talking about degradation, maybe, or it's good to know. This is actually from Alaska, published by Misha Konevsky, Yuri Shurer, and co-authors. This cliff is about 30 meters, almost 100 feet tall. And you can see that from their work, in many places, it's up to 95%, 95% volume filled with pretty much clear, or not clear, but pure ice. There's sediments involved. So now imagine 100 feet, all ice melted, 90%. So only, 10 feet will be left out of all this big cliff. So that's kind of what you keep in mind when you think what will happen to the landscapes when this kind of ice-rich permafrost will be thawing and ice will be melting. All right, now go back to temperature first. So in the past, when I started to study permafrost in mid-70s, there was no global warming. It was actually global cooling, you probably remember. And all media was excited about new ice ages coming. Well, at that time, we were still excited about studying permafrost as a geophysical kind of matter subject. But in that time, we were thinking about big changes between glacial periods, interglacial periods, like tens of thousands of years time frame. It's still very exciting, but it's mostly kind of academic interest. But all permafrost science was developed during this from 50s to 70s, most of it. And the assumption was that permafrost is permanent. That's why permafrost was its abbreviation of permanently frozen ground. Well, fortunately for us, to make it more exciting even, climate started to change, and change in the direction which is definitely not in favor of permafrost. So warming, which up to now already very well established and exceeds some 1.5, 2 degrees warming in the high latitudes, globally maybe 1 degree Celsius warmer now than it was in, say, mid-20th century. And of course, permafrost reacted to this warming. So how do we know about it? Well, one more slide here about now it's kind of all averaged by global, it's red, and Arctic is blue, and that's what I said about how much warming happened. And you can also see that higher latitudes are reacting to this warming more actively, more amplifying, so-called polar amplification in climate. So that's why for high latitudes, compared to those 70s, we are like 2.5 degrees already warmer than it was then. Globally, it's still 1 degree warmer. So how do we know? Well, fortunately, in University of Alaska Fairbanks, Professor Emeritus Osterkamp, he established in the very, very beginning of this first kind of observations that were showing that climate is getting warmer. So he established a transect of relatively deep boreholes, like maybe 60 to 80 meters, about every 40 miles. And its transect goes from southern edge of permafrost, somewhere in Glen Allen, Kakona, to Prudhoe Bay, very conveniently along the highways, Richardson and then Dalton Highway. And and it was established in the early 80s. And since then, and on this map, these boreholes showed in the red square. Another big player in this game was U.S. Geological Survey, which used geological boreholes much deeper, like 500 meters and even deeper, which were used for geological purposes. But then, after they were drilled, temperature started to measure in these boreholes, and we also have very long record, about the same time. Some of them actually even earlier than early 80s. At some places like Barrow, there was some very good records of permafrost even starting in the second half of 1950s. So since I will be talking about our set of data, and now there's more players involved, actually. There's more organizations, federal and state organizations start to measure temperature and in the ground to see what's happening to permafrost. So we use some different sensors and different technique to record this temperature, but it's more or less standard. So we do this pretty much the same way in all these boreholes. And we have not only deep boreholes, which is here, it's about 65 meters borehole, but also we measure temperature, but with every hour, actually, in a shallower depth, down to 3 meters, 10 feet. And also we measure other things like air temperature, snow depth, soil moisture, and all these records, we collect this data to understand, well, first of all, how this temperature changes, and then why it's changing. And then, when we understand why, we can actually model it. So in our lab, we're not only measuring temperature, but we also do developing pretty sophisticated permafrost models, which you can predict, well, project how permafrost will change in the future, assuming one or another climate change scenario, of course, because again, climate is the driving force of these changes. So what's what kind of results? I mean, how do they look like? So very typical presentation of this data will be, so every year we do these measurements. This is in meters, so 20 meters to 55 meters in this case. It's a dead horse borehole near to the airport, like 5 miles south from airport in Dead Horse, Prudhoe Bay. And temperature was measured every year, but once a year. That's why we interpret only this part, because above 20 meters there is some seasonal variations of temperature, but below 20 there is no seasonal variations. All seasonal variations disappears in the upper part, and we can see this as a reaction to climate change. So it's kind of long-term changes. So it's very good for us because permafrost is natural kind of low-pass filter. So it filters all diurnal, seasonal variations, and then we can see the signal, the climate signal. That's why we can see it actually much sooner than atmospheric scientists or climatologists, because they're dealing with very noisy data of air temperature. So in permafrost temperature, all this noise already gone, and we can see very clearly what happened, what have been happening here. So it was a little bit of cooling after we start to measure it in the mid-80s, but since mid-80s, it was continuously warming and warming and warming. And if you look at 20-meter depth, it's already by now more than 3.5 degrees Celsius increase compared to mid-80s. So which means that, well, we made already at least 1/3 of the way, 20 meters to that zero threshold. The same data, this is our transect, and this is kind of the same data from boreholes at 20-meter depth, but as a time series, just to see it at one depth, 20 meters, but as a time series. And some actually measurements started in Dead Horse and Westdock even before that. So that's where you clearly see the increase in temperature in 20-meter depth. What we see here that in colder permafrost, this increase is larger. In warmer permafrost, it's a little bit lower, the rate of increase. And sometimes it happens that it's not really monotonous, but sometimes it could, or not increasing, or even a little bit of cooling, a little bit, like what we have very recently, because of two consequent cold winters in cold years on the North Slope. So let's see what's the explanation. So the main driving force here is still air temperature. So this is air temperature data from Barrow Meteorological Station, actually only first order meteorological station on the whole North Slope of Alaska. And we clearly see that it was a little bit warmer in the 40s and maybe the beginning of 50s, and then it was cooling. That's cooling what I was mentioned. The new ice age is coming. But since then, it was a very, very steady increase in temperature, with some variations, of course, from year to year, but a very, very significant warming. And now in Barrow, we can see the temperature is, well, amazingly warm, well, -7.5. For Barrow, it's definitely very warm, because typical temperature for all this period was about -12. And also, snow cover is another important player for permafrost, because snow protects permafrost during the cold period, winter, and then during the summer is not there. So more snow, warmer temperature will be in permafrost. So you always have to look at least at these two meteorological parameters to see what should happen to permafrost. And that's conclusion of our analyzing our data as well. Let's see, I'll skip that one. Now, of course, the more exciting to see what's the result of this warming, right? Even increase in temperature in permafrost, even if it's still more or less stable, it's already changing its properties. And in terms of engineering, it's already important, because, well, if you know, that's many buildings built on permafrost region on piles. So to hold these piles in the same place, permafrost should be cold enough. And that's how it was designed, how deep the pile should be. And if permafrost temperature is increasing, like I just showed, this capacity of holding of the same weight is decreasing. And that can make problems for infrastructure even without thawing of permafrost, just because of it's warmer. However, what we see also in even in cold permafrost, and I will give you example, very cold permafrost, that's this warming make it not only warmer, a higher temperature in permafrost, but also increase in summer thaw depth. So during the summer, because of warmer climate, the depth of thawing getting larger and larger. And eventually, remember these ice wedges? So they sitting here, and every year, of course, and before this warming, active layer, so we call it active layer, the layer which thaws every summer and then refreezes every winter, was more or less, the same level, say 50 centimeters. So that's why the most ice accumulated starting from 50 centimeters and down and below. Now we have deeper penetration of thaw, so upper part of ice wedges started to melt. And that's a very good example. This is Banks Island. Actually, it's even farther north. It's Mold Bay. It's in Canadian archipelago, where permafrost is minus 14 degrees Celsius, very cold permafrost. But because of during long time, the climate was such that summer thaw was not penetrating deeper than, say, 50 centimeters. That's why this top of ice wedges was very close to the surface. And now, because of this penetration, now we start to see degradation, we call it degradation or thawing, melting of ice on the top, and developing this kind of pictures. And you look from above, again, and this is Prudhoe Bay area, you can see that this warming and melting of ice started pretty recently, somewhere in actually the first melt was described in about mid-90s. So before it was more or less stable, and then you compare it's the same exactly area, high resolution satellite images, very high resolution, And you can see how this very nice and smooth surface with some degradation already happening, actually, because it's 90s, it's not 70s. But it's progressively increasing and developing these troughs and water bodies, completely changing, well, not completely yet, because it's only what we see now, it's only melting of top of the ice wedges. Only, it's not degradation of permafrost everywhere, so it's just local. But even this local degradation already creates very different conditions for vegetation, for animals, for people living there. And I want to give you this example, which we actually observe this process when it's just started in the Canadian archipelago. So we were lucky to establish these 3 sites. So the Prudhoe Bay is here, on Banks Island, and Mould Bay in Prince Patrick Island, and Isaacson in Edda Fringles Island. And this is about 78, 79 north. So we established these sites at time when everything was look like this. So nice smooth surfaces, not much of the any kind of troughs or anything developed. So in 2005, this is Isaacson, the farthest north one. So that's plot. It was set by biologists. They, of course, studied all vegetation, and I was responsible for temperature measurements. And so exactly the same plot here. This is the same plot, the same flags. Of course, they change color because 8 years changed. When we came back, when we were able to come back 8 years later, we found that surface is very, very different than it was at that time when we were there. And I will just show several of these photographs comparing what it was then we established and when. So it's then we revisited in 16s, and it got even worse. There's still water start to accumulate. This is the set what my station is ground temperature measurements, and actually it could be, yeah. So it was like this, very, very smooth and nothing particular. Well, what happened? We actually put it very close to the ice wedge. Well, we didn't know even because there was no indication there was any kind of ice wedges there. Well, and we were very worried when we put it that polar bears can destroy the station. Well, no problem with polar bears, but problem with degrading permafrost and ice wedges, because it starts to kind of see, it's already leaning on one side, and eventually with further development it actually could fall down. So very, very, very rough, uneven surfaces. And this is, I think, very good because it's the picture was, I specifically tried to take picture from the same position. So that's 2 hills there on the horizon. Kenji Yoshikawa, I don't know, you may not heard about him, was in the 13, and that's the difference. So very, very obvious, big, big difference. Again, permafrost temperature is -15 here, -15. So it's nothing, permafrost itself very stable. But because of just the beginning of thaw, beginning of increase in summer thaw, start to melt ice wedges and developing this kind of surfaces. 16, even more. Yeah, and see our tower is kind of tilting. Another one in dry place actually survived a little bit better itself, the plot. But big trough developed next to it. And in this about 11 years between this beginning and now, about maybe 2 feet of depression developed. And the same on other sides. I will just skip that. And explanation for that, you can say, well, how much of the thaw increase? it's like if you have 60 or 80 centimeters of depression, how it could happen? You cannot get this amount of thaw or melt of ice just because of warmer climate. So the problem is, it's not only a warmer climate, but also the surface is also subsiding. And the distance between ice wedge and surface is more or less the same, because melting ice wedge produces water. Water drains because it's kind of sloping area, and the surface is actually following the surface of ice wedge. That's why you can get so much of melt of ice in 10 years, up to 80 centimeters, which is for permafrost, it's a lot, because permafrost in general very, very kind of conservative, a very inertial feature. So, but that could happen, and that's our explanation. It's also because of these depressions, they can trigger not only settlement because of thawing, but also erosion. We call it thermal erosion, because it's not just water taking particles, but first material thaws and ice melts, and then water takes it away. So erosion, very, very common, that erosion triggered by this settlement because of melting ice. Also some slow processes like this kind of slide, which whole upper, say, 50 centimeters of ground together with organic layer on top just move down the slope. Very, very common right now. And exposing permafrost, and if permafrost is very icy, then you, and I will show some examples, develop these retrogressive thaw slumps, so-called thaw slumps. Just a couple more pictures how it looked like, like this, like carpet. That's retrogressive thaw slumps when it happened first, and then the ice was so much ice in it, and when it melts, because it's exposed, it melts fast, and the wall of this slump going towards the intact area, and involve more and more and more and more in this process. And it will go all the way like this until the ice, it will go some area where less ice in permafrost. And then it may stabilize and stay. But this is very, very common process, again, during the last 20 years. Those kind of things happened in the past as well, but they were kind of one and another one there and there. Now they count in this area, actually in North Slope and Canadian Archipelago by, I don't know, by many tens of them appeared, and actually new appear almost every year. Definitely changing locally, but changing environment very, very significantly, landscape very significantly. And of course some other negative consequences is this silt goes into water, it's affect fish. This is actually it's a Selavik river in Selavik slump, on this photo. Yeah, it's very good fish there, white fish mostly, and some other she fish, I think. So, and definitely it will affect some, I would say, people fishing, how much fish they can get because of the changes in conditions. Yeah, that's the development in time. This one, there's many, many of them. So I just want to show the last one, a mega slump in Siberia, of course. Everything is mega in Russia. Yeah. So this is the satellite image of this huge slump, which developed again during starting somewhere in the late 80s and the beginning of 90s. And it was, first it was small and then increased, and now it looks like this. So this is trees. It's a large tree, but it's kind of what we have, black spruce kind of analogy in this case. So it's at least 5 meters, maybe more, tall, the tree. And that's the slump. I mean, the volume of material was removed because mostly it was ice again. Now, it's still dramatic, but it's still local. It's still locally happening because of one or another thing, because of degradation of ice wedges or development of this retrogressive thaw slumps. Well, much worse situation will be when permafrost will start to thaw everywhere. So not just in some particular place, but pretty much everywhere. So in this case, we have to expect much more serious consequences for landscape change. So now, when it will happen? Good question, right? Well, we have enough data now to do some very simple estimate. And it's very, very simple. So we have this already, and I will show an example of dead horse location. What we see here is mean annual temperature of air temperature, mean annual, since mid-80s, when the latest warming actually started on the North Slope mostly. And also we measure, like I said, the ground surface and permafrost surface and permafrost in 20-meter depth. So that's what we see here. Surface red, permafrost surface blue, and 20 meters green. Mean annual temperatures. And that's what first time I made, I was brave enough to put this straight line. Just very, very simple model. Regression, linear regression, boom. And it surprised me a lot because, say, before we start to look and we collect enough data, everybody from permafrost community, they were strongly believe that permafrost on the North Slope of Alaska will be stable till the end of the century for sure. That was very, very common, and still common belief. I mean, Alaska pipeline still, when they did some renovation of the permit, they said, well, permafrost on the North Slope is stable. You shouldn't worry about it. Well, I was very surprised that actually the straight line hit 0 degrees Celsius at 250. And then, since then, we continue to collect data and see where it goes. Well, before last 2 very cold years, it was going right where it should be. Now, I'm not sure. Maybe we should move this this straight line a little bit, and it will give us another 5 or 10 years. But still, even that, 2060, it's not even, it's middle of the century. It's not the end of the century, and that's where our permafrost surface temperature will be approaching 0 degrees Celsius. Of course, there are some physical processes which will slow down because ice will start to melt partially. Lots of energy will go to it. It's definitely, at this point, the crossing 0 on my line. Nothing dramatic will happen immediately, but permafrost will start to thaw in maybe a matter of 10 years. So now, that's about cold permafrost, which we thought it shouldn't be any problems, but we already have some problems. And of course, on top of that, and if I will have time, I will show some examples in infrastructure. Infrastructure make this problem even worse, because infrastructure itself, any kind of buildings, pipelines, roads, they add to this warming itself. Just the construction of this infrastructure affect permafrost usually, if there is no special cooling, like it was done for Alaska pipeline, for example, then pretty much any kind of infrastructure will make permafrost more vulnerable for warming. So now, let's look what's happening here in the interior of Alaska. Well, lots of things too. So that's only sites in interior. College Pit, it's Fairbanks pretty much. Birch Lake, it's halfway to Delta Junction. Healy, Galkana, and Livingood. So for colder permafrost, we still have general warming. It was a little bit of up and downs until somewhere like 2013, 2014. It was warming and then cooling a little bit. But since then, we have very, very rapid warming in Alaska. And that's also right for Healy. Interestingly enough, that place like Livingood, where temperature already was minus 0.7, doesn't change too much. Well, there is physical explanation. In this case, temperature is not a good indicator of changes, because at this temperature in silt, which is pretty much what it is there in silt, ice in between the granules of the material starts to melt, even below 0 degrees Celsius. It's very well known physical fact, because of water, in this case, it has no free water structure. So it actually melts, ice melts at a little bit lower temperatures. The same as like under pressure, the same as like some impurities. It all make ice melt, like seawater, for example. It freezes at minus 1.8 degrees Celsius, not at 0, sea ice, because of the inclusion of seawater in it. So, and because of that, and this minus 0.7 is enough already to start to melt ice partially, a little bit, but lots of energy going into this process, and temperature doesn't change. It's the same as, say, I don't know, in school, our teachers always say this: you have cube of ice and cube of water, exactly the same size, exactly the same. And both of them at 0 degrees Celsius. And you start to warm them with exactly the same amount of energy. So what you will see, the water start to get warmer and warmer and warmer. The cube where ice was, it's kind of start to melt, but temperature is still 0, 0, 0, 0, 0, until all ice melted and became water. You know what? By the same time, with the same amount of energy, the water cube, which was water originally, it will be at temperature plus 80 degrees Celsius. 80 degrees Celsius. That's the difference between how much energy you need to put into ice to melt, compared to how much you can put energy you put to water or any other material to make it warmer. So big difference. So that's why even small amount of ice turning into water takes pretty much all this excessive energy which goes here in warming of permafrost. And that's why temperature is kind of warming, but not really. In this case, temperature is not good indicator of the state of permafrost. Probably we should, and we start already, measure the liquid content. So how much liquid water is there? And we obviously see that with temperature not changing too much, the liquid water content portion of water and ice, water is increasing and ice is decreasing. So that's probably a better indicator what's happening there. Maybe too much science here. But that's explanation. I'm trying to explain what, because the question is why there is not changing anything, and here is so much change. That's because of that. And again, if you look at the forcing, air temperature, mean annual air temperature at Fairbanks Airport Met Station, which we have records actually since beginning of 1900s. So it was again similar to actually a little bit earlier warming here, then cooling, and then step-like jump in about mid-70s. Since then, it was actually not much warming, even a little bit of cooling. And only, again, about 2013, 2014, we have new wave of warming, very similar to what we had here. So we don't know if it will sustain or it will go, but at least up to now, we have very, very strong warming in increase in air temperature, and that's how permafrost react. It's also get warmer. And more excitingly, of course, snow is also important, and that's why, for example, in the 90s, who remembers, beginning of 90s was lots of snow, much more than even last winter, which we will say, oh, it's lots of snow last winter. Compared to 90s, no. It was like 1.5 meters. That's when I bought my snowblower. And then we got the beginning of 2000s, almost no snow. Anyway, it's still useful. Okay, so now what happening here is very different from what happened in the North Slope. Even with all this warming, we still, remember, -4, -5, -3, but still minus. So around Fairbanks, it's LTR, Side Bonanza Creek LTR. Temperature at 1 meter in permafrost is really, really critically close to 0 degrees Celsius. Very close. And because of that, actually permafrost started to thaw. So it's a little bit complicated graph, but let's look at this part. Very, very exciting part. So because with all this warming, people in media would ask, there's lots of warming, where is the thawing of permafrost? I said, well, it should come, just be patient. Finally, this last warming wave in Fairbanks, and not only in Fairbanks, but in all interior, including Seward Peninsula, create the conditions where permafrost start to thaw, and this layer of thawing now is deeper than winter freezing. Look at the left side of this graph, which showing temperature at a little bit shallower depth and a little bit shallower depth, a little bit deeper depth. And you see that in the past, this is kind of normal behavior of stable, warm, but stable permafrost. Every time you have warm and thawing in the upper part, which is active layer, but then during the winter, it freezes completely frozen, everything frozen, and by end of the winter, if you drill hole from the surface of the ground down to, say, 15 feet, it will be all frozen. No thawed layer. What will happen when this second warm wave came, and that's actually happened massively in many locations I will show on the second graph, it stopped refreezing completely. And by the end of the winter, the frozen layer not reaching permafrost. And there is some layer in between. We call it talik. Talik, it's actually a Russian word. And now it's a scientific term. It means simply not frozen. Tali, not frozen. But that layer survived over whole winter. And you can think about this as a cardiogram, of permafrost. Din, 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 din. Kaput. So that's indication of that permafrost is start to thaw and develop this layer of non-frozen all over the winter, or year-round, actually. And of course, implications for that are huge. For microorganisms, for water, for vegetation, lots of interesting things happening. And eventually, if it will continue, this is already our modeling, this talik, or layer which is not freezing at all, will be getting deeper and deeper and deeper. And by the end of the century, this is again Bonanza Creek, it's Fairbanks site what I showed data. Depending on how much ice is in permafrost, it actually can be thawed by 14, 15 meters, which is 45, 50 feet, not frozen. And most of the ice, what we were discussed before, most of it is in that upper 50 to 30 meters around Fairbanks. So it means that, and this is a case where no ice, like massive ice bodies. We didn't consider that, because in case of ice, there will be a completely different story, because surface will be subsiding and thawing will propagate much faster, actually. destroying pretty much all landscape which is sitting on it. Like, I don't know if anybody visited Permafrost tunnel, right? So in Permafrost tunnel, imagine how much ice is there. And it's all somewhere like between 7 and 20 meters depth. So if this thaw will penetrate in this ice and it will melt, that will be complete reorganization of landscape, I would say. So it will be turned into muck, just. So that's what we are saying. Again, we are at a threshold where cold winters, low snow winters still refreeze this talik, this new developing talik. It's still possible. But a little bit later, when if warming will continue, like it was, having happened before this point, then we will go into the area where no matter what kind of snow you have, no matter what kind of cold winter you have, talik will survive and in this point it will continuously grow and grow and grow deeper and deeper and deeper. So that's pretty much kind of diagram to illustrate. So when permafrost is stable, you have this seasonally thawed layer. It seasonally thaws, but it's completely frozen by winter above permafrost. And then this is the point what we actually experiencing right now. So a little talik, maybe just 20, 30 centimeters in many cases, sometimes a little bit deeper, develop already. But in the future, if climate will be warming the same rate, so the permafrost the top of permafrost will be getting deeper and deeper and deeper, and only seasonally frozen layer will be there, because winters will still be minus 40. That's guaranteed for a long time. And during this winter, of course, some material will be freezing. But again, with warmer winters, which actually winters warming faster than summers, this layer thickness will be shallower and shallower. And in our modeling, by the end of the century, we have only like 15, 20 centimeters of frozen during the winter time. And that's what I promised you. So it shows where, so we have many sites. Those ones with deep boreholes on that map with squares, there's kind of maybe 20 of them, but we have about 300 other shallow sites where we measure temperature at the shallow depths down to 1.5 meters, down to 2, 3 meters. And in the latest work we just published actually on Monday in Nature Geosciences. That's a figure from it says in review, so it's published on Monday. So out of 54 sites we choose, which before this latest warming wave were normal permafrost, where active layer was freezing completely before. 54 sites we choose, not affected by any water, surface water, or fire, because forest fire also make conditions that make permafrost much more vulnerable. And usually it's thawing if it's severe enough fire. So out of 54, more than half of them showed this development of this talik. And it's true for around Fairbanks. It's true also in Salavik area. It showed the same in Seward Peninsula. So it's pretty much very, very common now. Again, some of them may refreeze by now, but about in 10 years, we will thresh this second threshold. We will cross this second threshold, and talik will be stable and continue to develop. Okay. I think I have a little bit more time. I have time. I mean, no problem, because typically it's an hour and a half class. So I can stay longer if anybody would like to stay. Welcome. And yeah, we need questions. I mean, we have to discuss what I'm talking about. What's for us? Why we should worry about this thing? Well, you know yourself. sinkholes, for example. Sinkholes is it's a very good example what happened when permafrost is thawing. Most of our sinkholes actually permafrost thawed a little bit earlier, so and now they just collapsing. So in some particular, because I said it's a whole range of conditions, right? And some places like what we choose actually cold places where we put our sites. It's kind of typically black spruce forest with some protective organic like moss layer and peat, so they're more stable. But there's lots of less stable, especially on the shoulder of road. This is the Gulfstream Road. So there, permafrost already was thawing after construction of the road. And developing this ice was melting. And because it's ice wedges, it's all this kind of structure, they connected to each other. And water was just simply draining somewhere, like to Gulf Stream probably, to the creek. And these voids, they develop during some time. And usually in the spring, when this roof of these voids get not strong enough, it collapses and create this sinkholes. But they are developing in other places more stable in the past right now as well, these empty volumes. We just don't see them before they collapse, but they are growing, sure. And this latest excitement about Birch Hill, big one. So yeah, it was not there probably maybe 20 years ago. I mean, the void, it all developed pretty recently, and now it's collapsed. Water going in and disappeared, never filled, because there is some channels. Yeah. And it's not my imagination. Actually, at the Geophysical Institute, when they were building this addition to Geophysical Institute, this verb called building, they dug very, very deep excavation. And we actually saw these channels there, empty channels. You can see it goes way. Nobody was brave enough because they're not that big. Well, actually big enough for a person to get in, but better not. So, yeah, it's younger me trying to reach the bottom. And usually it's like, like 3 meters, like, up to 20 feet easily. Kenji again. Sometimes it happens when it's a big ice wedge melts. It's actually on another side of the Stis Highway from that pipeline exposition, Steve Reeves land. When big ice wedge close to the surface melts, it's actually surface collapse, not just as a hole, but whole trench, huge trench. And we see it many, many places. That's another place. It's a Miller Road extension down the hill. So that's happening, and very recently. That's very recent thing. Fortunately for the owner of this house, this trench happened just about maybe 20, 30 feet from his house. Yeah, that's how it looks like. Also lakes, of course, thermokarst lakes are called. When ice melts and there's no drainage, then water accumulates and subsidence create this depression and water collects there. And water, of course, make permafrost thaw even faster. And of course, there's could be a lecture about methane coming from thawing permafrost, very, very exciting thing. Actually, I think impact on infrastructure much more serious than impact on carbon. Carbon, of course, global. So it goes out and it goes all over the place. Infrastructure, it's more local, you think. Of course, for us who live here, it's maybe more important than global things. But for people who live in, say, in the low 48s, in Alaska, how many people there? 800,000. It's okay. But for us, of course, it's much more serious. But I would argue that infrastructure, impact on infrastructure of thawing permafrost, it could be regional or even global problem because of lots of energy sources, I mean oil, gas, now going into the Arctic, into the permafrost, especially in Russia, but in Alaska as well, of course. And interruption of this flow of this stuff, you know that it could actually have, like we have now, global consequences in terms of fuel price and so. Now, just a little bit to finish. What we should expect in the future, very, very kind of briefly. Well, all bad news. Of course, all this bad news based on modeling, climate models, and some people believe more in them, some people believe less. But like my simple model, if everything will stay the same and everything will be changing like have been changing during the previous 35 years, which we observe, then we should expect significant warming in the future as well. It could be wrong, of course, because linear interpolation of present-day climate is not a good thing to do, but pretty much all climate models show that it should be warming anyway. So that's one of them, and shows that, look at these numbers, and this Celsius. So we should expect warming in interior somewhere like 4 degrees, 5 degrees, so like 7, 8 degrees Fahrenheit warming by the end of the century. And in higher latitudes on the North Slope, even more serious numbers. So of course, permafrost will react on that. And we do some modeling, like I said, and I will show just a few examples of this modeling on a global scale and Alaska scale. So according to one of our models, that's what we should expect. So it's present-day conditions, distribution of permafrost in the Northern Hemisphere. By 2050, all this red where permafrost will be thawing. So it's kind of simplified model, but even this simplified model shows that by 2050, interior will be pretty much thawing, which actually based on our data makes sense. And by the end of the century, only North Slope and this simple model, permafrost, it looks like still stable. However, with our other more advanced models, and actually warming scenario here was not extreme scenario, it was kind of average scenario. But in our more advanced models and more aggressive scenario, warming scenario, it shows that many places on the North Slope, permafrost will be thawing. Again, in agreement with my simple, straight line model. In Alaska itself, this is 1 kilometer resolution model, shows that by mid-century, again, here we already see that not that homogeneously disappearing. So there is some conditions where surface and vegetation and so conditions where permafrost will still be more or less stable. Not really, almost dying, but still there. But in most places it will be gone. And again, by the end of the century, only Brooks Range and North Slope, according to this model, which is not really extreme warming model, permafrost may be stable. And of course, there's consequences everywhere on the North Slope, in interior, for infrastructure. Now I'm talking about infrastructure will be very severe. So this is access road to the material side, was built during the construction of Dalton Highway and Alaska Pipeline. It was used that time, about 50 years ago or so. And then after that, it was not used. And that's what happened to the road if you just leave it like this in a relatively cold permafrost. So I'm saying that if our Department of Transportation will just give up on our roads, all our roads will look like this in about 15 years at maximum. Yeah, like this. Good example, it was 2015 flood at Death Horse, Pruder. And of course, permafrost was thawed and ice melted because of this flood. But you can imagine what will happen if it will happen just without any disturbances, any water, just climate. It will happen the same. See? This is Dalton Highway, this one. That's Dalton Highway, what happened to it. Of course, flooding is kind of very short impact and severe. Long-term thawing, there will be some time to fix, to fill. Like somewhere here around Fairbanks, asphalt layers already like 3 meters, 4 meters thick, just filling. And also very serious consequence could be for communities, local communities, coastal communities, because remember, settlement. And some of these communities, for example, Point Lay, is actually part of it sitting on that very, very big ice wedges permafrost. And because of the thawing, melting of ice, subsidence of the surface, actually area could be inundated by water. So orange is what will be left of land at the end of the century. So it is potentially very dangerous, of course, because they just will losing land. Not because of coastal erosion. Coastal erosion, of course, there. But coastal erosion maximum will be like, I don't know, 1-2 meters per year. Sometimes, of course, with big storm, it could be more. But we're still talking about 10 meters. You know, it could, 100 meters per century. Here, it's everything goes down, and water from. Well, of course, it's possible to build dams like in Netherlands. Yeah? Keep building and live below the sea level. I don't know. All right, and just a few. That's Fairbanks, very famous house. It's still there. Of course, nobody lives there, but this is behind Geophysical Institute. This is Russia, also Russia. And in the end, what I would say, little kids, little problems, and bigger kids, bigger problems. So, thank you very much. And much more information about our work could be found in, can easily remember, permafrostwatch.org.
How's the pipeline holding up? Are the GSM sinking, or are the heat exchangers, keeping up with energy?
Yeah, Alaska pipeline was designed with big kind of, let's say, how would say better? So with already assuming that permafrost could be unstable, especially because of construction, and these thermopiles, it's not just support members; they're actually refrigerators without any energy, of course. But it's very, very nice engineering design. You don't need energy to make them run. So make situation much more stable. So far, there was no major problems, There's lots of small problems constantly, and they are addressing it all the time. But problem is, two problems here in the future. So first of all, you keep permafrost around these refrigerators or thermopiles, but it's disappearing everywhere from landscape. And especially in the slope area, slope getting unstable, and you cannot do anything with this refrigerating your pipeline route. So that's big problem. It cannot be addressed as easy, well, expensive, but still easy for this local cooling. Second, also serious problem, that winter's getting less cold. So we don't have much more this minus 40 degrees like 2 weeks, 3 weeks, month. It's already shorter, and because of that, the efficiency of the cooling also decreasing. So just simply warmer winters, the same piles not cooling as effectively as it was during the design and so far. So future will bring more and more problems. However, like I said, it was designed very well. Actually, also very interesting story, because when first the company who was designing it was from Texas, and of course, what they do, they just dig the trench and put the pipe, and no problem. And fortunately, that's their proposal came through this environmental assessment through USGS, U.S. Geological Survey, and it was Art Luckenbrook. He's actually a very, very famous scientist. He's kind of one of the fathers of permafrost research in the United States. So it actually came on his desk, and he looked at it and he said, and he wrote just like 2.5 or 3 pages of review, and pretty much it says, "Are you crazy?" And fortunately, the government was brave enough to make this cost of this pipeline like 2.5 more expensive, but it's still working still, and definitely if it will be not that will be major disaster already by now, much earlier than now even. So it's a good example. There's many bad examples, like in Russia especially. And they built this new Trans-Siberian pipeline to China. And they did exactly that. They dig the trench, put the pipe, fill it, and there's massive problems right now.
Somebody did send in a question on our forum, and it's, what's the difference between permafrost and an ice lens?
Ice lens. Well, ice lens, it's just some volume of ice, more or less pure ice. And you can create it in your refrigerator. So it could be on the surface, like this winter especially, when it's rain during the Christmas time, develop this huge ice lens pretty much everywhere on the surface. It's not part of permafrost because it doesn't fit definition. It's first of all, in your refrigerator, it's not natural material, that's artificial. And on the surface, it's not survive 1 year. It's already gone by now. So what you need is ice lens. It could be a part of permafrost, but the main thing is that it should survive in the ground or near the ground. Actually, the ground better, because we don't want to fight with lithologists, with glaciers. No, there's much more of them, so we will not win. So, but below the ground, if it will survive 2 or more years, then you can call it permafrost, and if it's formed naturally.
So my question has to do with the air temperature data as kind of an approximation of how much warming might happen to the surface of the soils. Mm-hmm. And I'm wondering about radiative heat gain.
I'm sorry?
Heat gain from direct radiation from the sun. And it has to do with this shrubification phenomenon that the biologists are demonstrating, the increase in tall shrubs, increasing radiative heat gain, presumably being transferred to the soil.
Mm-hmm. Yeah, very good question. So, of course, the air temperature is a driving force. It's a major driving force. But between air temperature, air and permafrost, there are several layers. Vegetation layer, organic layer, peat, active layer, material, and depending on properties of this, and some of them seasonal, snow cover also in between. And each of this layer make this transition from air temperature to permafrost much more complicated than just simple, the same amount of air temperature increase, the same amount increase in permafrost temperature. No. In some cases, yes. In some very simple environments like bedrock somewhere and almost no snow, that will be pretty much the same. Radiation, it could actually have some role I would say it's still limited role, because a surface usually warmer during the daytime because of radiation. It's colder than air temperature during the nighttime. So on daily average, it's already very close. Snow surface, it's also pretty much daily average will be very close to air temperature. So for that, we can, of course, in a very good model, it actually take into account this energy exchange. Now with shrubs and shrubification, it's even more serious problem, not only because it's changing albedo and because of that warming more, but also in more because of trapping of snow, especially in the tundra area, where in Fairbanks it doesn't matter because we don't have pretty much wind. But in most permafrost areas, there's pretty strong wind. And any kind of shrubbiness, increase in shrubbiness will increase in thickness of the snow layer, because trapping. And you would say, well, if it's trapped here, so it came from somewhere else. Well, actually, during the snow drift, lots of it sublimates. So you actually, with shrubs, you gain total amount of snow, because it's less sublimation is going on during the drift of snow. And this increase of snow depth, because of shrubbiness, it's much more serious warming factor than changes in albedo. And we have it, we have data in Seward Peninsula especially. And it's interesting, and I'm asking biologists all the time, we very often see the snow depth is about the same as shrub tall. And I said, where's the chicken, where's the egg? If shrubs don't want to grow above snow because it's cold, or it's just because as much shrub is there, the much snow will pile up. So nobody answered these questions yet for me. And I am a geophysicist, so I cannot say anything about shrubs too much. So, but yeah, shrubification definitely will be factor of destabilizing permafrost and make it much warmer.
Thank you again very much. Thank you all for coming as well.